Hello, everybody. So let's continue with our machine learning cohort. Second week, second day. Today we are going to do a lab, or we are going to learn about calculus, the calculus part of the things that are used in machine learning. All right. Before going into the details of the things, just let's quickly revise that how do we take the differential of a function. Let's say function x is equal to x squared. How do we take the first order differential of it? If I take rho to dou x of x squared, what will be the value?
X.
2x. Right? So n, any variable raised by n minus 1. Right? If I take rho to dou x of a log x, what will be the value?
1 by x.
1 by x, that is absolutely correct. All right. If I take dot to dou x of e raised by x, then what is the value? You can Google it.
X into e power x minus 1.
Is that correct? All right, let me know if you find out, okay? All right, but let's stick to this one. Huh?
E to the power of x.
Dot to dou x of e to the power x is what?
E to the power of x.
E to the power x, okay? Just over. Okay, so if I take, let's consider this function right here. If I take the first order differential, that first order differential is 2x. If I take the second order differential of this, then what will be this? That is basically dot to dou x of 2x will be equal to 2. All right. If I take the single derivative of x squared, what does it represent? Geometrically, what does it represent? Anybody? For a function.
Differentiation.
Yeah. If I take differentiation geometrically, what does it mean in English for this function?
The slope of
the slope. All right. Slope of the function. It represents slope of the function. All right. If I have a function like this, all right, at any particular point, if I am considering this and this another one, then this slope is represented, this difference. This slope is represented by the first order differentiation. Make sense? So if I want to take, let's talk about a concept of numerical gradient. It's called numerical gradient, or we can call it a scalar gradient also. Numerical oblique scalar gradient. That is, gradient is nothing but the first order differential of our function. If you're taking notes, gradient is nothing but the first order differential of our function. If I want to take first order differential of a function fx, then how can I take the first order differential? What does the differential represent? Remember, it represents the slope geometrically. But if I don't know the rules of the differential. Over here, we knew the rules of the differential, how to take the differentiation. But if I don't know the basic rule of differential, oh, this is dou by dou x is of x square is equal to 2x. If I don't know that, what's the naive way of finding it?
How does fx change with a small change in x?
Perfect. How does fx change? And that is the conceptual meaning of the differentiation also. That with a small change of x, how does the fx change? So I can write it like this also. Fx plus delta x minus fx. Since I have increased the size, that if I divide it by delta x, then that should be giving us a first order differential of x. And first order differential of x is nothing but gradient. All right. So in order to do this, this is from x, I take a one step ahead. This is called the forward differential. If I take the central differential is taken like this. That is, I take one step forward and I look at one step backward. So total units is 2 delta x, right? This is called central difference for finding the numerical gradient or the numerical differential. The advantage of this is that it is more accurate in the sense because it is able to remove the first order errors. I might be having some errors because I have delta x over here. Since I have minus of delta x over here, the first order errors or the noise can be removed. Now, remember this. This is what we will be implementing for numerical gradient. But why does numerical gradient, why do we need to be worried about the numerical gradient in the first place? If I already know how to calculate the differential of any of the functions, why to bother about this? The purpose of the numerical gradient is that we can validate our findings of the gradient that we are taking with the first order derivative like this. This is a good validation point for that, okay, this is the numerical gradient if we are able to find this like functionally. Then with differentiation, whatever we are finding, we will be able to validate it to the numerical gradient that we have essentially found mathematically. We are not implementing any differential over it. A small change in x is what is being told by the numerical gradient. All right. So let's go into the first step of the lab, that is finding the numerical gradient. All right. Firstly, we have imported the numpy, and now what we are trying to find out is the numerical gradient of a function fw. If it is fw, then we are doing fw plus delta w minus of fw minus delta w divided by 2 delta w. This is essentially what we are doing, that whatever we have written on the whiteboard. A small step in the forward, a small step in the backward direction. All right, so how do we do it? Okay, let me reset it. So firstly, w is equivalent to the x that we have written over here. All right, we are creating a range for the w. We have a random number generator already declared right here, seeding from 0. We are having a w. We are having 5 values. Let's print w first. All right, this should not be giving me the right answer, but let's try to see how does W look like. It looks like 5 values in the standard normal range. All right. Then what we have defined a function. Just by looking at this function, can you tell me what is the function? How can you define the function in your terms?
It is sum of square of the elements.
Sum of square of the elements. Make sense? Sum of square of the elements. All right, we'll see. All right. So firstly, I have a W, which is NP as array. This is just a guardrail that we have a W, and we are declaring the data type of it as a float. Although we had a float array only, this is just a guardrail. We had a W, which is already a NumPy array of floats. And then what we are doing is we are taking a gradient vector. Remember, W is a vector of 5 elements. If I want to have a gradient vector, I'll declare it np dot zeros like W. A NumPy array of 5 elements filled with zeros. This will be telling me the gradients. If I want to take the gradient of 5 elements, all right, we have declared this as 1, 2, 3, 4, 5. All right. It's a vector of 5 elements. Then essentially, if I want to take the step, then firstly, I'll keep the others constant and I'll take a small step in this direction first, or for this index first. Then I will keep this one constant, and I'll take a step in this direction. For implementing that, what we have done is we have declared a NP array that is just equal to E. You can call it step array also. And if you see clearly over here, then we are declaring that EPS is equal to 1 e raised to power minus 5, which is basically the step, the small step, a very small value of whatever. All right, over here, then that will be added to the first weight, and we will see the change. Then we will keep this constant, and I'll increase the step in this direction, 0.00123. Then I'll keep this and this constant, and this constant as well, and I will make a step in this for this weight. So if I have a weights vector of 5 elements, W1, W2, W3, W4, W5, we are one by one, we are taking a step for each and every weight.
हाँ वो कॉल पे है
All right. So for that, I have declared, we have to declare a E for firstly I in range of, I will be going over number of elements of my W, and I'll be declaring E as np dot. This is the result. This is the gradient vector, okay? Gradient vector. Numerical gradient vector. Huh? All right. So once we have declared, then firstly, for E is equal to I will be declaring that for which index we are taking a step. Make sense? All right. Now, my G of I, gradient of ith index will be equal to what? Remember, this is what we have to do. That is functional value of W plus E into EPS minus of functional value of W plus W minus, sorry, step back E into EPS. All right. Once we have found this complete thing, I have to divide it by 2 of EPS. Why? Because one step in the forward direction, one step in the backward direction. So let's see essentially what we are doing over here. We are declaring an E which is equal to 0, 0, 0, 0, 0. For every W, I am declaring this. If my W index is equal to 2, then I am filling that E with 1. I am multiplying that with small step EPS. So this becomes very 0.00123. Rest everything is 0.000. Now what we did, we just added that. So this remains constant. This remains constant. Step in the forward direction. If it's step in the backward direction, then we are doing this, minus 1 plus 0, 2 plus 0, 3 plus this small step, delta x.
Sir, one
Next.
question. How did you select the EPS value?
Yeah, so it is just a general convention. You can take the EPS value other numbers also, but very small numbers. All right.
Okay.
All right.
But it can
So-
be anything other than what you have provided.
Yeah,
But it
you
has
can
to be
take
this one.
it, you can take it at EPS is equal to here I have taken e raised to power minus 5. You can take e raised to power minus 6 also. All right.
Okay.
Don't
Do
take
you
it
have
10.
any-
Don't
Okay.
take it 10. All right.
Okay.
Very small value. All right.
So the EPS value is the step we are moving towards.
Yeah, that is the delta x or the delta that we are moving. Just the step.
Okay.
But this E is making sure that we are taking the step in for one weight only. If we are considering the ith weight, we are taking a step in that direction only. All right. 2 into EPS. All right. Now, once we have found the gradient vector, I'll be returning the gradient vector G. All right. Let's see what are the mistakes that I'm doing. If I'm running it, it passes all the test cases. But for this thing, that let's see what is the gradient number. That is the numerical gradient that we are finding for function f. That is print gradient number. All right. So if I print this, if I run this, then it is this value. If I print this, W over here, did I remove this print G number? All right. Make sense?
Sir, one question. In the function, we pass the W, that was
Mhm.
array, and we find the gradient. So means I understood the function, but here the gradient is sort of a slope on those elements. Is that we are calculating?
Slope on the function f.
For each value that is written, right? That's a slope for each value. Because
For
corresponding
for the slope at where the current W is.
okay, corresponding to that value means we have 5 values. On those we have found the 5
On
slopes.
that, so if I'm representing a curve like this, if I'm given this W right here, all right, on this curve, what is the slope at that point of time? This will be represented by a certain point now.
Got it, sir. Yeah.
In our
Thank
in our lab right now, the W value, 5 values are defining where that curve is. What's the point of that curve? All right.
Okay. Thank you.
I want to see you to observe something over here. If I'm printing W and printing gradient of the number, then you see something special about these.
The signs are in the same.
Twice.
The signs are same. Okay, what else?
Twice. The values
Yeah.
are twice.
Nice.
All right, these values are twice. The second, the gradient number is twice than that of the weight values over here. Can somebody explain me why is it twice?
So the equation is square.
X square. This is square. So if I take our own differential dou by dou x of x square is going to be 2x. So all I had to do was multiply all these values by 2. So something is correct in our numerical gradient. Make sense? All right. Now comes the main part of that how do we implement? This is just the numerical gradient. Still we are into the mathematics space. But now let's dive into the calculus space. And in order to dive into the calculus space, we are going to look at the applications of the calculus as well. All right. So we were talking about, so in order to see the value of the calculus, we will be talking about linear regression and logistic regression. Just remind me quickly that what kind of model is this? For linear regression, what kind of target that we are trying to predict?
Numerical value.
Numerical value. All right. It is numerical. Perfect. Correct. And what kind of model is a logistic regression model?
Classification.
Classification. Specifically, 0-1 classification, right? Binary classification. All right. Now, once we are, how do we model linear regression? What is the underlying assumption of the linear regression? That if my y is my target, then how do we express y?
Wx plus b.
W plus b plus some y. All right. Let's forget them for now. Wx is the way. That is a linear equation. The numerical target is going to follow a linear model. That is the underlying assumption of it. And we are given an X input matrix which has features in the columns and samples or data grains in the rows. And one of the columns will be target. Firstly, we will be dropping this. We will be training our model on these features. If I have these features as x1, then w1, x1, w2, x2, w3, x3, so on and so forth. We are trying to find out the weights of each and every feature that we have. x1, x2, x3, x5, 4, x5 are the features. We are trying to guess out what will be the weights of all these features. Basically, we are trying to find the w1, w2, w3 over here. Initially, since we don't have any input of the weights, and in machine learning, what we do is we guess out. We take a random guess. We take a random guess of the weights. With that random guess, we are trying to find y predicted. Remember, there is an actual column that we have dropped, which is y actual, y true, y actual. Once we have, with random selection of the weights, we have found out the predicted values of y. Then we go about and find something called a loss function. That is the error between my predicted value y and the actual value of y. That is the error function or the loss function. Error or the loss function. The error and the loss function dictates that how should I be changing my weights? How do I adjust my weights? Then I adjust my weights. Let's say the model has 2000 iterations. In the next iteration, I adjust the weights. The adjustment of the weights, I calculate the y predicted again. I have the y actual again. I again find the error. Based upon that error, I further adjust my weights. I means me, I am the model. All right. So in each iteration, I keep adjusting the weights so that my error is minimized. This is the basic philosophy how the machine learning model, linear regression machine learning model is running, or any kind of machine learning model. Now for linear regression, I can have the error or the loss function in many manners. We can have different loss functions. But we have talked about one loss function till now. And that loss function is what? Yesterday we talked about it.
Mean squared error.
Mean squared error. Mean squared error. And to Euclidean. All right. We can have RMSE also. Root mean square error. We can have mean absolute error also. These are L2 based and this is L1 based. Manhattan. When we take the absolute values and we take the difference between them. These are the different loss functions that we have. Now the critical thing in a function or in a model is that I have found the loss function. What is the loss at a particular time? I had some weights. With those weights, I predicted something. I calculated the loss with my actual y, actual target. But the first thing that the model will be asking or I will be asking is, hey, I have to change the weights. But in what direction? How do I change the weights? What should be the adjustment? And for which weight I should be making the adjustment? Now, in order to answer that critical question, that how should I be changing the weights? In what direction? What magnitude? We will be talking about a special error, that is mean squared error. Just remind me that, okay, if I have to find the mean squared error, how do I find the mean squared error at any particular time? Anybody who can guess out? Mean is 1 by n, right? Right? If I want to find sigma of I is equal to
A dot B
1
upon
to n, we'll talk about it. Let's go 1 by 1. You are absolutely right though. That is y hat predicted value minus y actual y value at that ith index, at ith position, ith sample. All right, square of it. We are not taking the square root over here. In the log, we will be taking the square root. We are taking the square of the errors. Square of each and every error divided by n is going to give me mean squared error. Now, there was a question in the class yesterday that where will I be using L2? Where I'm going to use the L2. That is, I'm going to take the distance like this rather than absolutes. All right. And we were able to talk a little bit about this. Now, I'm going to modify the question in the first place that, okay, that why I should be taking mean squared error at a particular time in my model. Why not RMSE? Or why not the absolute error that we are taking? Why not I take the error like this, 1 by n, I is equal to, this is absolute error. Huh? No squaring the things. Why to take this? How is it this beneficial? In what kind of situation you will be taking mean squared error? Let's say your data is like this.
outliers.
And you have a prediction linear model, you have fitted like this. So if it is a mean squared error, the outliers which are at a very high distance they will be contributing because we are squaring the distance now. The outliers will be punished very heavily. The penalty for the outliers is going to be high. If I want the penalty to the outliers pretty high, then I am going to use something like mean squared error. If I don't want the penalty to be high, I can go for the L1 or Manhattan distance error. Now this is squared. Make sense? Just the geometrical visualization. Can somebody tell me what is the graph of a quadratic function? What is the graph of a quadratic function?
Ellipse.
Ellipse. Is it like this? Just Google it.
A bell, maybe like a curved.
A bell like this?
Parabola, I think.
Yeah, it's a parabola. It's a parabola. All right? It's a parabola. So now you know that, okay, why I was drawing a bowl-like shape over here. Earlier also. It was square also. That was also quadratic. It will be something like this. A convex kind of bowl. Where right here, the error will be minimum. Not zero, minimum. And if this is my x-axis, this is my y-axis. Just remind me one more thing, before I talk about the axis, that okay, this is error, huh? Value of the error, or the loss function. The loss function curve is like this, because it's quadratic. What should I be writing over here? How are we changing? How is this loss function changing? Based on what?
Weights.
Weights. Remember, we are changing the weights and we are finding the next error. We are changing the weights and we are finding the next error. So this is changing according to the weights. If this is the loss function, let's call it L, then if I am able to find dl by dw, that is, how is the loss changing according to the weights? That what is the slope of that? Then my life is sorted. And this is called gradient. That if we are right here with certain value of my weights, those are 5 weights. If we are right here, if I am able to find the slope, that is this, or this plus delta, a little step into this direction. This is what is represented by dl by dw, first order derivative of my loss function. Then this gives me an information that how should I be increasing or decreasing my weights? And in which direction? In which magnitude? And that is the advantage of the calculus. It basically gives me the slope of the loss function, which is changing according to the weights. Now, if I want to find dl by dw, this is the loss function, right? This is the actual value of y. This is the predicted value. If I take the predicted value was predicted according to what? It was predicted according to, at the single place, the loss is, if I forget about this for now, is y hat is nothing but xw. Xw, and this is y squared of. Make sense? Now, if I want to find the gradient, let's do dl by dw. All right. If I want to find dl by dw, if I am able to find out the differential on this function, then I will be able to know what is dl by dw. That is the gradient. Just to tell you that the gradient G, if I'm defining it as G, gradient will be equal to 2 by n x transpose xw minus xw minus y. This will be the gradient. Now, most of the people will be telling you that, okay, oh, this is the gradient. That if this is the loss function, then this will be the gradient. But let's try to find it by ourselves. Let's try to prove it so that you don't stay worried or you don't say that, oh, by magic, I am getting this gradient. Let's do the differential, and if I'm doing the differential of this loss function, then I should be getting this. All right? Okay.
How did I get n by? Oh, okay, got it.
Mean. Makes sense. So okay, if I define this 1 by n, if I take this as residual is equal to y hat minus yi. Y hat is nothing but the prediction, which is we are then doing using the linear one. Extra. All right. So I can write the residue as xw minus y, the actual value of it. So if I am taking the loss function is basically 1 by n of r square. All right. If I'm taking differentiation of the loss function with respect to the weights, that's what we need to find out. Then this is equal to dr by dw. We can write the differential like this, right? Very famously, it is called something. And in machine learning, this rule is used a lot of calculus. What is this rule called? Whether it is neural networks, whether it is regressions, anywhere, logistic regression, any kind of regression, or neural networks also. We do this, we expand the differential like this. What is this rule called?
Chain rule.
Chain rule. This is called chain rule. So if in order to find dl by dw, I just need to find dl by dr, dr by dw. All right. So let me focus one by one. What is dl by dr? If a loss function is differential of with respect to r of 1 by n r square. N is a constant. All right. So if I take it out 1 by n, this is 2r. All right. So we are getting to some point. 2 by n into r. All right, this is the value of my dl by dr. dl by dr is nothing but 2 by n into r. And remember the r is what? xw minus 1. Okay. So we have this, we have this. Now, if I am able to find out what is the value of dl by dr by dw. Remind me, what is r? R is nothing but d by dw of xw minus 1. Why is the true n? It doesn't change with respect to w. With respect to weight, my actual value, only my predicted value is changing, right? This doesn't change. If I take this, then what will be there? D by dou by dou w will be equal to xw, and this will be 0. All right. So if I take this will be changing according to the w only. I'm left with x1. So one of the terms give me dl by dr gives me 2 by n into r. The other one gives me x. I have to multiply both of them. If I multiply both of them, then I will be having x 2 by n into r in x into r. Okay. What is r? Again, xw minus 1. So I have this, I have this, I have this also. But this is transpose. All right. So we have reached, with the chain rule, we have reached that, okay, this is the way that I can get the gradient. Basically, it is the first order differential with respect to the weights, which we expanded according to the chain rule. And first of the chain and second of the chain, we are calculating it. And that gives me this. Only except the transpose over here. Got it? It's essentially this only. So we are not, this is not magic. This is just basically first order differential. Just tell me, can somebody guess me why I'm taking the transpose over here?
To make the matrix stable, like let's say 5 cross
No.
5, so multiply.
No. Is Darshan there?
Yeah, I don't know actually.
Yeah. This is a question that you had asked yesterday only, right? That why are we taking the transpose over there? All right. Whenever we have the shape mismatches, we have to match the shapes. And I told you that, okay, whenever we were talking about xtx now and xty, that I have to match the shapes. All right. So wherever you see the transpose, then you are trying to, it's a golden rule that we are trying to match the shapes. Now let's do step by step, one step at a time. That what is xw? It's a predicted value of y. What is y? It's actual value of y. Tell me, is it a matrix or is it a vector? And if it is a matrix, then what is the shape of that matrix? If it is a vector, what is the shape of that vector? Go back to how your initial data is structured. Remember, the table is like this. Features, samples, and one target. Y is what? Target vector. A single a numpy array of n over it. So the shape of this is nothing but n. And x is what? Our input matrix. What is the shape of input matrix? N into d, where d is what? Number of dimensions or number of features. N is the number of samples. If I'm going about multiplying this matrix with the vector, not a vector multiplication, matrix with a vector multiplication, do the shapes align?
You need to reshape first, right?
So you have to transpose the first shape, and it has to be. Hence, X transpose over here. So that we can align the shapes. If I'm aligning the shapes, now that matrix vector multiplication is possible. Hence, from here, I just adjusted the shapes so that I can take the transpose, so that I can take the matrix vector multiplication. This is step-by-step guide of how do we get to this gradient, right? Anybody, any questions?
Sir, one question. So in that sense, if we take any matrix and we take its transpose for any multiplication, it's equivalent. We can take, just we have to match the shape.
It depends upon whether you are doing the matrix to matrix multiplication, matrix to vector. It's not one rule fitted for all. Make sense? So if you are doing the matrix to matrix multiplication, then if you are doing M1 into M2, that is matrix to matrix multiplication, you are thinking that, okay, if I inverse this matrix, will that be same? It might not be same. Makes sense? But here we are multiplying a matrix with a vector. Does it make sense?
So we can do with vector. We can play this thing with vector.
Yep. All right. I'm not sure about this. All right. I think it should not work.
Yeah, I think because the values would be again a matrix. So value depends.
Okay, let's try to code it out. That is, if we are given, it is there. If you want to see the complete derivation, the steps that I have listed are there on the Substack also. Okay. If I want to find the MSE for the linear model, and the MSE is nothing but 1 by n sigma of y predicted minus the y actual squares. All right. So that is the loss. And if I want to find the gradient is, this is what we have just proved, right? All right. So if I have to return a function which is giving me the loss function as well as the gradient. Okay, so initial values, that is x, we have taken an n by d, and we have taken as 20 length. Number of samples and 4 features, 4 dimensions. The weights will be equal to the number of dimensions. So it has to be standard normal range of d dimensions. Then y is also going to be 4, right? Oh, sorry, number of samples, which is going to be 20. Y vector. It's a 1D vector. All right. Loss and gradient is what we are calculating this using this function. All right. Then genome is our numerical gradient. And we are trying to find out whether the numerical gradient at this weight we are finding is pretty close to the gradient that we are finding using the differential function that we are. Differential function gives me this thing. Are they equal? Are they close? So numerical gradient is coming into the picture for validation that the gradient that we have calculated over here is correct or not. So if I have to calculate the loss function over here, the loss function is nothing but the loss is, and in the end we are going to return the loss and the gradient. All right, loss is nothing but 1 by n into np dot sum of, how do I write this? Y hat minus y. There are two ways. NP dot linear algebra dot norm of xw x. Okay, let's take the x at the rate w minus y xw and y and whole square of it. All right, this is one of the ways that I can do it. But what's the other way? How do I do it in a naive manner without using the linear algebra? Is np dot sum of np dot x. Okay, let's take the square term over here. Square term is x at the rate w minus y. All right, this is not the square term yet. This is, we have to square it. All right, this is the residue. Let's call it residue r. This is the value of the residue. Now what we are going to do is residue square. All right, so this is a vector, remember. So we can do r into r. That should give me the square of this. We take the sum of it and we divide it by n. That can be the loss function. All right. Or alternatively, I can write the loss function as np dot mean of r into r. Make sense? Residue into residue. We can write it like this also. Okay. But let's go to the gradient now. Gradient is equal to, if I want to find out the gradient will be equal to nothing but 2 by n. 2 by n into x dot transpose and multiply it with the, not multiply, matrix multiplication it with the residue r. All right. This is the way that I should be finding out the loss and gradient. Okay, let me just confirm it. N is, okay, I forgot to take n. N is nothing but x dot shape 0. The first of the element of the tuple of the shape will be giving me the number of n. All right, and r is nothing but, this is fine. The loss is, I could have done it like this also. I am doing it like this also. This should also work. And gradient is nothing but, it's a float. This can give us an error. Okay, 2.0 divided by n, multiplication with x transpose, dot product with r. Not dot product, matrix multiplication with r. All right, that is the residue. And we are returning the loss at the gradient. Okay, let's try to run this. This works perfectly fine. All right, this should work, and this should also work. Cool. And we are able to validate that it is pretty closer to the numerical gradient also. Make sense? So all we did was that in a computer sciencey manner, how do we write the gradient as well as the loss function? That at this particular position of my weights, what's the loss? And at this particular point of my weights, what is the gradient? So that I can adjust the gradient tomorrow. The next iteration can adjust the gradient. Next iteration can do the gradient step. Gradient step is nothing but adjusting those weights. Make sense? All right. This is for linear regression. Let's just quickly do it. Remember, we will keep adjusting the weights at some place. The mean squared error will be minimum, and after that it will start increasing. All right. We will be giving our model certain number of iterations that keep decreasing, keep decreasing, keep decreasing. When it reaches right here, then we will be able to. And after that, it starts increasing. The model will be able to detect, oh, this is the minimum point, and it will be one global minimum. This is the first order derivative of my loss function. So gradient is first order derivative of my loss function, which gives us the slope of this curvature at that particular point. Just tell me one more thing. It's a little advanced thing. But if I take the second order derivative of the loss function, if the first order derivative was representing the slope, what will be the second order derivative telling us? Anybody? You can tap GPT. It will be telling us that how that shape, how that slope changes. If the first order derivative gives us the slope, the second order derivative tells us how does that slope changes. For example, slope is very steep over here. It starts decreasing right here. The slope starts increasing right here. The change of the slope will be giving us, the second order derivative will be giving us change of the slope. If the change of the slope over here is steep, 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 less decreases, less decreases, less decreases, less increases over here, then change in the slope is nothing but giving us a measure of curvature of that loss function. Make sense? So first order derivative tells us the slope of the curvature. The second order tells us the shape of the curvature that we have. Make sense? These things will come into the picture. The first order derivative, we called it gradient. The second order derivative, we will start talking about it when we go to the advanced stuff of the models, and it will be called Hessian. All right. Just warming you up with certain terms. Okay, now this was the linear regression, but we are left with the next step that we have to do is the logistic regression also. That we have to find the loss function and we have to find the gradient in the logistic regression also. All right. If you go into the last week, we had a derivation in which we developed the model that, okay, the logistic regression under the hood follows a linear model. All right. We still have XW. But what follows? Remember, the logistic regression is a classification problem. If somebody remembers from last week, what did we say? That, okay, there is certain things which are going to follow the linear model. What is that certain thing called? It was called log odds of success. There is a special name for log odd of success, log odds of success, log of odds of success. The special name for that is, see, those things will keep coming back. All right, we'll keep revising it till the time you guys are don't get ingrained in your mind. Those things are called logits. The basic assumption of the logistic regression is that the logits are going to follow the linear model. That is, log odds of success is going to follow the linear model. And if we go back to that derivation, then we said this is nothing but odds of success. Probability of y is equal to 1, provided x. Y equal to 1, provided x. Odds of success is nothing but probability of y is equal to 1 if we have x event. Probability of y is equal to 0 if we have x event. Since it is a binary, if y is equal to 1, if y is equal to 0, I can write it as 1 minus probability of y is equal to 0, but y is equal to 1, provided x, which is basically this thing. And we discussed about this thing that in a lot of situations, especially for probabilities, we take the log curve. Why? Because log curve is able to tell us, is able to do the scaling of the probability, which is going to be between 0 and 1 only, very small values. But the basic assumption of the logistic regression is that the log odds of success is going to follow a linear model, XW. And when we further, we take log on the other side, that is e raised by XW, P 1 minus P. I need to find out at a particular position, at a particular sample in my X matrix, what is the probability of something happening. My prediction is probability of something happening. Y is equal to 0, y is equal to 1. Y0 means customer doesn't churn, y is equal to 1 means the actual value of y, the customer churns. So at each and every sample or the data grain, we are trying to find out whether the customer will churn or not. What is the probability of him churning? Maximum value of him churning, 0. Maximum value of him, probability of him churning, 1. Minimum probability of him churning, 0. So probability, when we take this on the other side, it was 1 plus E x raised by W. Let's call it XW as Z. E raised by Z. If I take the P on the other side, then it was 1 minus E raised by Z is equal to E raised by Z. And when we took, this is from last week only. You guys have forgotten, that's why I'm writing it again. All right. And when we divide this, everything with E raised by Z, then this became 1 by . This was called sigmoid function. All right. Sigmoid function was written like this. This probability is nothing but sigmoid function of Z is equal to 1 over 1 plus E raised by Z. This is the way that we are structuring our logistic regression. Sigma Z, this is called sigmoid function. If it is multi-classification, then rather than sigmoid function, the function will be softmax. Remember, in one of the left, we had talked about softmax. All right. This is the logistic regression's basic function. Now, if at any place we are predicting the probability of this happening with this, where Z is the linear model, XW. Then we have to calculate the loss. In linear regression, we define the loss as RMSE, MSE, mean squared error, root mean squared error, mean absolute error, different kind of errors. What can be the potential loss function in logistic regression? Remember, now it is a classification problem, and we are detecting the probability. This is the predicted probability. The loss function in Logistic regression is called BC. Binary cross entropy. All right. But more than the name, what really matters is the loss function at a particular sample, for a particular sample, not all the samples. For a particular sample, it is minus of y log of p minus of 1 minus y log of 1 minus y. Now, once you see it, once I saw it for the first time, it was very confusing to me. I had two confusions. One, why is it negative, negative? In front of each term, why do I have negative, negative? And why do I define the loss in this manner only? All right. Now remember, the p is between 0 to 1. What is the log values of between 0 to 1? Remember, we had seen the log curve. Yes.
Negative.
The log values are negative. Just to remind you or warm up your nerves again with the log function, log curve. Remember, this was the log curve. All right. Less than 1, everything is negative and it approaches minus infinity. Make sense? Log to the base e. Just look at this green line. At 1, it is equal to 0. Log of 1 is equal to 0. So the negative or negative in front of this is explained by this, that values less than 1, the log values are negative. But let's go into the details of this. The better way to understand this is, how do I calculate the loss? If my p is the predicted value, if my p predicts that, okay, that the churn probability is 0 and the actual is also 0, is there any loss? Is there any error? Is there any error in my prediction than the y true? None. No error. So my loss should be equal to 0 in that scenario. Let's see it. Since y is equal to 0, the first term is 0. All right. If I go over here, 1 minus 0, log of 1 minus 0. What is log of 1? 0. So the total loss is 0, which is perfectly correct. My loss should be 0 if my predicted value is 0 and my y value is also 0. If my predicted value is equal to 1 and y is equal to 1, let's look at that. Then log of 1 is 0. First term becomes 0. If predicted value is 1, log of 0 is minus infinity, but y is equal to 1. 1 minus y becomes equal to 0. So I have no loss in this scenario, which is conceptually correct, because both my prediction and the y value is absolutely same. But if my predicted value is 0, that the customer will not churn, and y is equal to 1, the customer actually churns, there is a lot of loss in that scenario. So let's look at that scenario. If y is equal to 1, this is minus 1 into p is what? Log of p is, log of 0 is minus infinity, which becomes plus infinity. The first term gives us a very high loss. Makes sense? And if I take, forget about if I take 1 minus y over here, that will be 0. But the loss has come from the first term. If I flip, if my predicted value is 1, but the y value is equal to 0. Remember here, the first element gave us the loss, and which was pretty high loss. All right. In that scenario, if y is 0, this gives me none. This gives me minus of 1 into log of 1 minus 1. Again 0. Remember, log of 0 is minus infinity, minus minus becomes plus, and I have an infinite loss, which is absolutely correct. Makes sense? So the justification of the conceptual understanding of this This is called binary cross entropy, or famously, we will not be saying it BC again and again. It's called log loss. Log loss is the loss function of my logistic regression. It is expressed like this. So this is the loss function. If I take dl, first order derivative of this, remind me one more again that I will be taking the loss function derivative with the what?
Weights.
Weights. Remember, we are changing the weights. The whole idea is that have the one weights, predict the values of the target, compare with your actual target, adjust the weights till the time your loss function is minimum. So with respect to weights, dl by dw, if I am able to successfully find dl by dw over here for this loss function, whatever blah 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 we have, then our life is set. If this is the loss function over here, that's how they define in our lab that the loss function is this. We are just right till here. Now we have to find the gradient of. All right, gradient is nothing but the first order derivative of this loss function. The gradient will be equal to 1 by n x transpose p minus n, where p is the predicted value. All right. So now let's go from here to here. Remember, 1 by n has to come. This was for one sample. This was for one sample. If I take sigma of all the samples divided by n, that would be the total log loss. I have to take dl by dw over here. If I have to take the dl by dw, remember, we can write it like this. This is linear regression. Okay, now comes the derivation of. I can have the chain rule and I can define it like this: dl by dp into dp by dc into dc by dw. Okay. This is nothing but the chain rule for dl by dw. If I am able to figure out these three terms, then I am able to figure out the gradient of dl by dw. Make sense? So let's go one by one. Firstly, dl by dt. What is log loss function over here? That is this. Just before going over there, before going to the gradient, what is the shape of this curve? MSE had, it was a quadratic function. What is the shape of this function right here?
Inverse of the log graph.
Inverse of the log graph. Okay. Inverse of the log graph. Log graph is like
Mirror image around the x-axis.
mirror image among the x-axis. Okay, that is correct. If I take the mirror image of this, again a convex shape like this. That's why both logistic and linear regression loss functions are called convex models, because the logarithmic curve is also like this, inverse of the logarithmic curve. So that's why I didn't delete it, because it will again be convex. The shape will be a little bit this thing. It will be like. But essentially, we are trying to do the same things, adjusting the weights and coming to the minimum BCE in this scenario. Now we have to calculate this dl by dp, differentiation of loss function with respect to p. All right, if I take, this is the loss function, n is the constant. I am taking 1 by n initially over here. If I am able to find the d of differentiation with respect to p of y log p, and 1 minus y log of 1 minus p. All right. So in this scenario, it will be equal to y, it will be constant because everything is changing according to the p. Y by log p was what? This is minus I in front of both. Okay, that is minus y by log of p differential with p is nothing but 1 by p. Same thing I have written over here. Okay, the second thing that we are going to write is this one, that is minus of minus of 1 minus y. Log of 1 minus p is what? Nothing but
1
log
by
of
1 minus.
is minus 1 by 1 minus p. The differential of log of 1 minus p is nothing but minus 1 by 1 minus p. So minus 1 and 1, this becomes positive, and this is nothing but 1 minus p. So dou by dou p of my loss function is nothing but, if I take minus y by p minus 1 minus y divided by 1 minus p. I can write it like this. This is the first term. We are expanding it according to the chain rule. Now let's look at the second term. We'll come to the second term later. Let's go to the third term. Dou by dot w of z. What is z? xw, remember? Linear function. If I take, then dz by dw is nothing but x. So I have the third term also. The third term is dz by dw is equal to nothing but x. Now, if I want to find the second term over here, differentiation of the probability with respect to z. Make sense? What was probability? Remind me again. Probability was nothing but, or sigmoid function was nothing but 1 by 1 plus e raised to power minus. So if I plug in 1 over 1 plus e raised to power minus z over here, then this comes out nothing but p into p divided by 1 minus p. This is the second term. So we have first term, we have third term, we have second term, right? So if I combine all three of them, then let's try to combine all three of them. Let's first combine first and second. That is minus y divided by p into 1 minus y, 1 minus p into p into 1 minus p. If I take this as the common denominator over here, then it will be p into 1 minus p, which will cancel with this. All right. So minus of y minus yp minus of p plus yp. Yp cancels. And I'm left with p minus 1. I just plugged in p minus 1 and this 1 by n, the third term, x and p minus 1. X is ND. Probability vector is, or the target vector is D on and on the sorry. Hence, I have taken the transpose. And we reach that the gradient is step by step by step. Does it make sense? This is, you don't need to go into the detail, but you just need to find out that this is not magic. The gradient has not come as a magic. It has come as a differential of my loss function with respect to w. That w has been chained to the, with the chain rule, I have 3 terms. I am finding those 3 terms one by one, and I'm just multiplying them, which gives me this gradient.
Where did the n come from? Sorry.
Say that again.
The n part, where did the n come from?
Number of samples. Huh? The
Yeah,
step,
where did this come from? Which?
the loss function was actually sigma of this now. This was the loss function. That was the loss
Okay.
function at a particular sample. At a
Okay.
particular sample, this is the loss function. But if I'm taking the total loss, that will be 1 by n of sigma of this. Right? So if I take the differential of the total loss function, the 1 by n will be coming. Make sense? So this is the gradient. So whenever we are talking about, and this is the shape of my loss function, and we are doing essentially the same thing. We are adjusting the weights. Wherever the minimum BC is there, we will be stopping our iterations over there and we will be giving those weights. Let's try to see it. Again, gradient is what we will be using. Gradient step is what we will be using for adjusting the weights in our model. So this is the crux that when you write your sklearn.logistic regression, what is going on under the hood? Honest? Okay, let's write I'm going to go a little bit fast over here. One thing that I forgot to mention. Remember the log loss when we were writing it or when we were finding it. This is negative one. This is loss. When we were finding it, if the probability, my predicted probability is 0, but the actual classification is 1, we had certain amount of loss. How much was the amount of loss? If my prediction is 0 and the actual is 1.
Infinity.
Infinity. Makes sense? If I am working with the infinities, then I might be having issues, right? So I need to have something called that I am operating within the range. I don't want my probability to be, my loss to be infinity. So that if I am working with that loss, then I have some numerical instability in my computations. If numerical instability is there in my computations, I need to take care of it. So we will be taking care of it rather than just the loss. We will be doing something called stable loss, which will be accounting for the numerical stability also. All right. So first and foremost, I'm finding the sigmoid function. Sigmoid function is nothing but, remember the sigmoid function? Sigmoid function is sigma of z is equal to 1 by exponential of minus z. Makes sense? So let's calculate the sigmoid. Sigmoid is, all right, 1 plus 1 divided by 1 plus np dot exponential of z. Now we are calling it stabilish kind of, almost stabilish sigmoid. All right. It's not actually, yeah, minus z, sorry. All right. It's a stabilish kind of sigmoid. It's not actually completely stable because if my z is very, very negative, then e raised power z goes to infinity, right? If you have to do the ideal situation, then you have to take care of the ideal, then you have to take care of the that situation also, that numerical stability also. But we will be returning the sigmoid over it. Now we have to calculate the loss. Just writing it over here. What is the loss? Loss is nothing but log loss is equal to this thing over here. All right. Is equal to, I'm just taking this, I'm writing over here. On the whiteboard, we have already derived it. Okay. Let's find the P first. What is the probability? If I call the sigmoid function on my x at the rate w. All right. xw will be giving me the value of z. Z is nothing but xw. I will be finding the probability with the sigmoid function, which I have already written. Now, once we have found the P, after that, I have to adjust the P. Just a moment. Okay. I'll take the EPS is equal to a small adjustment, small numerical adjustment. I'm writing it as Z is equal to X into W. Matrix multiplication, matrix vector. So this will be equal to Z. And I am making an adjustment for the P clipped. That is, we are clipping the probability between this very small value. Remember, my loss was infinity when probability was 0, and the other value y was equal to 1. It was infinity when probability was equal to 1, and the other value, that is y, actual prediction was equal to 0. Both the situations. So I want to have a range between, I want to keep the value of the probability between the range, that is 1 e raised minus 12, not 0, a small positive value. And on the other side also, 1 minus this very small value, so that it is not perfectly equal to 1. And we are not having infinities as my loss. All right. So I am not taking the P, I am taking the P clipped. All right. For that, I'm using the NumPy function of clipping. All right. Take the original probability and clip it between this and this. That is, if it is 0, then it will be giving us EPS. If it is 1, then it will be giving us 1 minus EPS. All right. Now we are all set. Let's find the loss. Loss function will be equal to minus of 1 by n into np dot sum of y into log of np dot log np log of p, np log p, and plus, I've already taken the negative sign in front, okay? But this is the log function. Loss function is always negative log function. Negative because of log between 0 to 1 is negative. So 1 minus p, 1 minus y. Y is the actual label into np log 1 minus p. Not p. I'm making a mistake. I should not be taking p. I should be taking p clipped for the numerical stability. All right. This should be my loss function. Let me just confirm if it is correct. All right. I forgot about the float. That's fine. I'm taking mean over here. That is also fine. I can do it like this also. 1 by n into np dot sum. All right. So they are taking as a mean. We can take it as a mean. That is sum divided by n is nothing but the mean. All right. Then this is y into np log p clip plus. Perfect. Seems to be fine. Now we have to talk about the gradient. The gradient is nothing but, we have already derived it on the whiteboard. The gradient is nothing but this. All right. So if I have to do it, gradient is equal to 1 by n into x dot transpose matrix multiplication with matrix multiplied by p minus y vector. All right. This should be the gradient. And in the end, all I need to return is the gradient and the loss. All right. So
will we not use p-clipped?
We should use p-clipped. Absolutely correct. Thank you so much. P-clipped minus 1. All right. So I'm just going to define the random number generator over here, so that I can do it again and again, and I get the same data. Where is the random number generator? Right here. Rather than right here, I am defining right here, so that in the scope of the things. All right. Now, if I try to run this code, failed where? Setting an array element with a sequence. line 7. So issue over here. Okay, so I think this should be float. Yep, 1.0. 1.0 plus np dot exponential of minus z. This is fine. If I run this, still an error. That is setting an error. Line 28. 28. Numerical gradient of. Not right here. There is some issue right here. All right, let's compare it. I have not calculated n. Yeah, we are not given n over here. So I have to calculate the n first. N is nothing but x dot shape 0. Okay. If I run this now, still an error. Only length 1 array can be converted to Python scalars. Okay. Let's try to debug the code till then over here. But let's try to compare it with the actual solution. Let me print P first. If this is correct, if the sigmoid is coming to be correct, should be correct. Yeah, P is correct. Till here, everything is fine. And P dot clip. Is the issue right here? Let's try to check, take this. The issue right here. No. Issue is right here, not right here also. Is the issue right here? I don't think so.
I think it's using P there instead of P clip in the gradient.
That should not have, even if I'm using P, still it's giving me an error, right? Ideally, I should be checking P clip. Just a moment, okay, let me debug it. There are two core bugs. Oh, it's not the machine learning that I am making a mistake at. It's the basic algebra BODMAS that we are making mistake at. Yep. The mistake that I am making over here is right here. All right, the operator precedence over here. Okay, well, that is first of the bugs. And the next bug is bug B. But you want, oh God, I did not have. I am returning gradient and loss and gradient is what we had. That's why it was giving an error at line 28 when we were unpacking it. All right. So 2 errors. If I run this works perfectly fine. All right. So this is log loss and the gradient in the logistic regression. We will actually be using it when we will be building the logistic regression. We will not be using any what do you call? What is sklearn? And any modules or the any modules of machine learning, we will be actually building these things. All right. Okay, now let's come to the next part, that is Hessian. This was the first order. And generally, for all the models, you will be able to, for example, for logistic regression and linear regression, logistic regression is basically the bedrock for the neural networks also. All right. We are also be using the logits over there. The normal logistic regression or any models can be done using just the gradient step. All right. Basically, if I am taking the slope, we are taking the slope like this. That is this step, then this step, then this step, so on and so forth. But the second order derivative is sometimes there is an issue that when we reach the least error, whether it is MSE, whether it is any kind of error, when we reach the least error, then it may be possible that we have a probability of overstepping that minimum, overshooting that minimum. So in order to not shoot that minimum, rather than taking the gradient step, we can take a Hessian step along with it, which is basically a very small step in that gradient step. Imagine it like this. If with the gradient step, you are skipping 100 steps or 100 units in between, and you go to the next set of weights. Then 100, step of 100, then step of 100, then you step of 100, step of 100, and you go to the minimum. Then you have a probability that you will be overshooting, right? Now the Hessian step or the second order derivative tells you the curvature, how that slope is changing. So you can take a further in a step of 100 units. I'm defining 100. It's not 100 is very big. The gradient step is very small. But if I am taking a scale of 100, if it takes 100 units, then gradient step is, the Hessian step is going to take, the gradient step takes 100. Then imagine the gradient or the Hessian steps takes just 1 unit. A very, very small step in that direction. So rather than 100, it will be taking 1, then 2, then 3, then so on and so forth. And we will be converging to our minimum error in a very, very small steps, and will not be overshooting it. In logistic regression, in sklearn, they say it Newton's method. You can actually specify that is what is going to be your descent algorithm. If it is a Hessian step, the 3 things, W plus gradient step is the normal. Along with that, if we have a Hessian step, then we will be taking this as constant, then I'll be changing the Hessian steps. 100 Hessian steps, then I go to the next gradient step. This is what we do with the second order derivatives. We take even infinitely small step of my gradient step. What can be the, okay, if it is very, very small, I should be using Hessian everywhere now. Why do the models actually use the gradient steps? Gradient only. Why not Hessian? Can you think about it logically?
We don't want too much accuracy.
We actually want really good accuracy. No?
But the
Remove
time
outliers.
Computation power. One, it is slow. Another, it requires a lot of computations. Make sense? One, it is slow. Another, it requires a lot of computations. All right. So generally, you use gradient step only. But in the models where you know that, okay, I need to take infinite small steps, then in that scenario, you can take the Hessian also. But this is the conceptual understanding of Hessian. But how do we calculate the Hessian? If my numerical gradient is nothing but f of W plus delta W minus central difference of 2 delta W. if this was the numerical gradient, then the Hessian we can take as a second order derivative of loss function. Like this, huh? I can calculate it like this with differentiation. But numerically, how do we calculate? Numerically, how do we calculate is that if this is the numerical gradient and this is represented by a function fi, then I find fi, this term right here, plus delta of this term right here, plus fi of this term plus minus delta of this term, this step right here, first order derivative, divided by 2 into delta of this term. All right. So this step, delta of this step, plus minus delta of this step, divided by 2 of delta of this step. This is the way that we can calculate the Hessian. Hessian will be a matrix. If I want to calculate it, this is the way that we are going to calculate it. All right. Okay, I'm going to just tell you about this. Weights is, we have defined the weights. It is a 4 by, it is a vector of 4 elements. If I print it, all right, it will be 4 elements. Then if I define a function, which is again, just tell me one thing. If I have x square, first order derivative is 2x. The second order derivative is nothing but 2. All right. So if I print the Hessian matrix in the end, I should be having 2, 2, 2, 2, 2. Make sense? Just let me print. In the end, if everything is correct, if I print the h, all right, then my Hessian matrix should be 2, 2, 2, 2. In line with our thinking, that first order derivative is that weights multiplied by 2. And the second order derivative is just 2. All right. But how do we find it out over here? So this is just to tell you that, okay, it is in lines with what we were thinking. X square is 2x and next derivative is 2. So we define, we are take the number of dimensions from the weight size, or I can do shape 0 also, same thing. All right. Then we are defining a Hessian matrix, which will be d by d. 4 dimensions, 4 by 4 matrix. Then what we are going to do is we are going to go over each and every weight. Remember, we are going to take the second order derivative of this weights. All right. So now inside that, we are defining a function. Remember, this function, then we are taking delta of this term, this function, minus delta of this term, this function, divided by 2 of delta. Basically, what we are taking is, if this is the numerical gradient, take the numerical gradient of the numerical gradient. Because it's second order now. Take the numerical gradient of the numerical gradient. So we are defining the gradient over here like this, just the way that we had done earlier. That is defining a step vector as number of dimensions. Then each and every step we have to, we cannot do the step in each and every weight direction now. At ith weight direction, we are having a step of 1. 1 into EPS. Huh? Again, EPS is over here 1 e raised to power minus 4. Very small value. I can take minus 5 also. All right. Just the idea is very small value, very small step. So we are taking a very small step in the, for V, where V is the original value that we are given. All right. And divided by this thing. This is basically the gradient, numerical gradient. Now, next step is for getting that Hessian vector at that ith position, all I need to take the numerical gradient of alpha. Numerical gradient we have already defined earlier at the first section. Make sense? So all I'm doing is a numerical gradient of the numerical gradient right here. If I give it this, then it will be giving the Hessian vector at that ith index. All right, that is what we are returning right here. This gives me the second order derivative. If I run it, this should be working absolutely fine. And if I'm printing h, it will be almost 2, 2, 2, 2. Make sense? This is what we are doing in the Hessian matrix, which is basically numerical Hessian, which is basically the numerical gradient, again taking the numerical gradient of the numerical gradient. Make sense? This is, you don't need to write it, you don't need to prove it, you just need to understand this is the second order derivative of my loss function. And this whole jing bang was to prove you that, oh, this is the second order derivative. Why? Because I have 2, 2, 2, 2, 2. And if I had a function which is v square, the first order derivative was 2v, the second order derivative will be 2 only. And identity matrix of 2's. All right. We are done with the class. Anybody has question can stay. Anybody doesn't have questions can leave. This is the calculus. The few things which you have to understand about the calculus is just finding the normal differential of the functions. Other one, that understanding the first order differential is the slope. The second order differential is actually the shape of your loss curve. And in order to develop or that loss function, or sorry, the gradient is the first order derivative of the loss function. And it doesn't magically happen that I get these values of the gradient that okay, it is 1 by n into something. All right. It is just nothing but a normal first order differential of the loss function. All right. And understanding and making yourself putting into the shoes of the libraries that you will be using, that what under the hood these libraries are actually doing. Firstly, calculating with the random weights, what will be your predicted target, taking the loss function and subsequently reducing that loss function to the minimum. And how do I know that in which way that I should be reducing my weights or increasing my weights or which direction to move is given to you by the gradient step. If you want to have further very small of the gradient step, then you can take the Hessian step. All right. Are you getting a feel of how the models will be building? We will be building. Anybody, any questions? Awesome. Bye guys, have fun.